Let us start. Now, yesterday we have gone through yesterday we have gone through the thin circular disk, the thermal stress induced in thin circular disk, as well as when thermal stress induced in thin circular disk when the disk is solid, there is no inner hole, and when the disk is hollow, means there is a inner hole and outer hole is there. We have assumed that there is no stress induced in the longitudinal length of the disk, and the stress induced only in the radial distribution, and stress and the temperature gradient, means the rate of change of temperature is only happens radially from 0 at the center and maximum at the outside, like this. Now, let us go through again for this. We have got yes. Let us go through another item known as long circular cylinder. Here, we will consider the nature of thermal stresses induced in thermal stress induced in a long circular cylinder. What is the nature? Nature of thermal stresses induced in the long circular cylinder. When the temperature is symmetrical about the axis, temperature is symmetrical about the axis means there is an axis for any cylindrical object, and symmetrically temperature is varying uniformly in both sides of the axis itself. Temperature is varying uniformly from in both sides or all sides of the longitudinal axis. Now, and it does not vary along the axis, means it don't have along the axis means the axis from one end to other. It does not varies along the axis. Axis means does not change longitudinally. Now, if the z-axis of the cylinder, z-axis is the axis of the cylinder itself, r is the radius, then r is a function of radius alone. And just one thing, then T, the temperature, is a function of R alone and is independent of Z. So, as per our assumption, temperature is varying along the radius of the cylinder and is not varying along the length of the cylinder itself. Temperature is not varying. Temperature is not varying along the length. Now, since the cylinder is long, sections from the end can be considered to be a state of plane strain, and we analyze this problem with UX, axial displacement assumed to be 0. So, cylinder is supposed to be comparatively long, so section can at the ends can be in a state of plane strain, and we can analyze this problem with UZ, that is displacement axial displacement along z axis or longitudinal axis is assumed to be 0 itself. Once again, owing to symmetry, all the linear stress components are 0. All the shear stress component of 0. There is no angular twisting or torque exists in the along the cylinder, and only 3 normal stresses, sigma r, sigma theta, and normal stresses sigma and sigma theta is exist. Sigma normal, sigma theta, sigma r, and sigma z. Stress along the radius, stress along the circumference, and stress along the longitudinal axis. Longitudinal axis, there is no change in temperature, but there may be stress in that stress developed in the along the length of the cylinder itself due to a change in temperature along the radius itself. The stress relation is now given by epsilon r 1 by E sigma r minus gamma into sigma theta plus delta theta plus alpha theta itself. Things are like this. What we are having here, a long cylinder it does not have any change in direction, change in length along the axis or along z axis. But stress sigma z can be induced. Temperature staging is staging along the radial direction or radially. We have three induced stresses, three induced thermal stresses, sigma z along the length, sigma r along the radius, sigma theta along the circumferences. There is no change in length along the longitudinal axis. And that is Uz is equal to 0. There is no displacement along z axis, no displacement along z axis. Now, thus we have three strengths, sigma, sigma theta, sigma z. The stress relation will be epsilon r, elongation along the radius, is equal to divided by 1 by r, sigma r minus nu divided by sigma theta, sigma plus sigma z plus alpha into t, where alpha is the coefficient of thermal coefficient of expansion, t is the temperature gradient along the radius, nu is the Poisson's ratio we know, and E is the Young's modulus, all we know. This epsilon, there is a elongation or change in dimension. Epsilon theta is a change in dimension, which works in the same way. That is the first sigma theta. Sigma theta, a change in dimension along this circumference means circumferential trend in circumferential strain and epsilon theta, and sigma theta is the stress reduced in circumference direction plus minus nu plus sigma r stress in the radial direction plus sigma z stress induced in the longitudinal direction plus alpha into t. Same sigma z means change in length in the longitudinal direction along the axis is equal to 1 by epsilon into sigma z minus gamma into sigma r plus sigma theta and plus alpha t. Now what we have is here we are told that is uz is equal to 0. So epsilon z, it is not epsilon z, it is the uz by the length. Epsilon z is the displacement uz divided by length of cylinder. It is also equal to 0. So from the last equation you can modify sigma z is equal to nu multiplied by sigma r plus sigma theta minus alpha t into alpha itself. So if we substitute the value of sigma z in the expression of epsilon r and epsilon z and epsilon theta, then we get epsilon in terms of 1 minus gamma square after simplification, 1 minus nu square by e multiplied by sigma r minus nu by 1 minus nu alpha theta plus 1 plus nu into alpha into theta, alpha into t. Hence epsilon theta 1 minus nu square by d epsilon sigma theta minus nu by 1 minus nu into sigma r and plus 1 plus gamma into nu into alpha into t. Now let us assume that 1 plus sigma r into sigma theta nu into e is 1 plus sigma nu into e is equal to one expression or one constant, you can say, that is e1. Gamma nu minus 1 by nu, which is given here, here, and here, which is equal to nu1, and 1 plus nu multiplied by alpha is equal to alpha 1. This is totally here, coming from here itself. So, okay. So if you put this constant or this expression in these two equations, you will have epsilon r 1 by e1 into sigma 1 r minus nu1 into sigma theta plus alpha 1 into theta, and epsilon theta is equal to 1 by e1 epsilon theta minus nu1 minus multiplied by r sigma r plus alpha 1 into theta. Now, so if we compare this expression with equation 10, what we have in equation 10, just quickly have a look at it. Equation 10 is given here. Equation 10 is given here, which is epsilon r into 1 by e to sigma r minus nu into sigma theta plus alpha r sigma theta 1 by nu sigma theta minus nu into sigma r plus alpha t. So this is similarly to equation, but just difference is the value is the e, nu, and alpha 1 nu. So we are replacing this thing and we got a relation of the same appearance. Thus we got the expression of epsilon and epsilon in the plane strain is similar to those in the plane stress. And if we use epsilon 1, v1, and alpha 1 in this equation, as per this equation, have in place of e, nu, and alpha, then the equation of equilibrium is in the case is the same as in the case of plane stress case. Further is identical to that. Is identical to that in the plane stress case itself. The expression for E1, the displacement in along r direction, sigma r, strain induced in r direction, and sigma z, strain induced in r direction means radial direction, and sigma z, strain induced in the along the leg, can be written in from equation 14 and 16 accordingly. What is it there? What we have 1 minus sigma, 1 minus nu, 1 plus nu, 1 by nu, multiplied by alpha into 1 by r. Equation is changed from r tends to a tends to r, the t into r into tr, c1 plus r into c2 by r, where a is the inner radius and r is the radius at the constant radius of the concerned point under consideration. And sigma r stress in radial direction is given by this full equation like this, and sigma theta is given E by 1 minus mu 1 by r square and so, just as in the figure itself. This is we have achieved in equation 14 and 16 like this, just having a quick equation 14, 15, 16. This is 14 here. This is the direction of r, and this is 16, and this is 15, and this is 16, as we have already discussed how this will form here like this. The same thing we are using here, except for n1, u1, sigma 1, nu 1, and epsilon 1 itself. They are different. Now, thus we have got this three equation, and this three equation we can have this from the equation of from this equation here. This is 29, this equation, and this equation, and 23 is the equation here. The equation relation between sigma r and sigma z and sigma r and theta. In this three relation, if we take within this, we will get the value of sigma r, sigma z in terms of sigma z minus alpha et divided by 1 minus gamma into 1 plus 2 into gamma 2 into nu e c1 1 plus nu into 1 minus 2 nu. Now, when T is equal to 0, at the point there is no temperature, this equation becomes identical. Where T is equal to 0 means this expression is equal to 0 itself, and only this expression, right side of this equation remains. Then this equation identified the equation already given, established in this chapter here. And normal stress given by this 30 is generally keep Uz is equal to 0. There is no displacement, but there is a stress induced here. The constant C1 and C2 are determined from the boundary condition, which are now considered these two particular cases. So everywhere we have to find out what is C1, what is C2, and so that we have to clear first two in order to use this equation. Now, this last hospital's rule, what we have, limit r tends to 0 is 1 by r, and integration from 0 to r, t into r into dr is equal to 0, which means what we are having, say, a elemental ring of radius of thickness around the diameter is only dr, and if we multiply it with that stress dr into r, and you have divided with bar, it will give you the temperature quotient at a distance r itself, and we are saying that this is equal to 0. Hence, what we have, that C2 here should be equal to 0. Otherwise, UR should be infinite and R is equal to 0. So, what we have here in the equation, in this particular equation here, if C2 is not 0, you have some order as some value, then when R is equal to 0, this portion will become equal to infinity itself, which is not possible. That you cannot, doesn't exist a deflection which is infinite in value. So we have to say C2 is equal to 0 here. So we have to left with the finding out the value of C1. Now, since sigma r at the radius equal to 0 at the center, r is equal to b, and then at r is sigma is b, then we get 28. C2 is equal to 0, alpha is equal to a is equal to 0, is the lower limit of the integration. So there is no hole here, so only the external radius, and we are saying that there is no stress induced at the outermost radius of the cylinder itself. And as C2 is equal to 0 and at A is equal to 0, there is no hole inside. Then the lower limit of the integration will like this. It is equal to 0 to B TR R dr 1 by d square, and C1 will become 1 plus gamma into 1 minus 2 gamma into alpha 2 plus nu is 1 by d square, and integration 0 to r t into r dr. So C1 will take this particular form 1 plus gamma 1 minus 2 gamma from the numerator, alpha went here, and in denominator 1 minus gamma as it's here, and this square, and this integration of TR into TR. Now, with this value of C1 obtained in the plane stress test, we observe that C1 for the plane strain then obtained from C1 for the plane stress. So, just changing E and mu and alpha to E1, mu1, and alpha itself. So, then converting this equation, the value of alpha r and alpha sigma is given right here. Sigma r and sigma theta, value of sigma theta I already sigma r and sigma theta is equal to alpha into E and 1 by B to mu square. Actually, this is common to the equation alpha E and gamma, so it is written outside here and here, and others are kept inside, and that will get into form 1 by B square 0 to P TR into TR, and 1 by R square 0 to R TR TR. Same this case sigma theta. So we got these two relation between sigma r and sigma theta. At r is equal to 0, at r is equal or r is equal to center, what will happen? Sigma r is equal to 0. Sigma theta will also equal to 0 is equal to that there exists only this portion of the equation, and both are then equal to 0. Then there is at the center, both the equations are radial direction and radial direction in circumferential distance are equal, and they are alpha into r, alpha e into 1 minus gamma, 1 by b square into t into rtr minus 1 by half into t into 0. Because if we put the value of r in somewhere here, all here r and here r, and this will become this portion. If we cancel this portion, will become 0 without making it infinity itself. So 1 by b square is 1 by 0 to b t into r, and minus 1 by half tmt into 0, where t is the temperature at r is equal to 0. Now, further from the equation 23 we have seen earlier, alpha sigma z is given by the relation alpha into e divided by 1 minus mu into 2 into nu divided by b square. This is 0 to comma sigma r dr minus t. Thus, the radial distance is also use the same formula for UR and put the value of C1 and C2. We'll take this particular form here, and like this 1 minus gamma etc. 1 minus nu the r by b square integration of 0 to r dr and 1 by r 0 to r dr into dr. Now, after we got the value of sigma r in this particular equation, we should assume a plane strain condition with x star z is equal to 0. So we'll understand our initial assumption was there is no strain along the length. Consequently, stress distribution sigma r is given with this stress distribution sigma z as given by equation 30 will are necessary to maintain if sigma z if z is equal to 0 itself. So uz or however, if the ends of the cylinder are free, then the resultant force in z direction should be equal to 0. So in that case, both the potential P uz will be available, but sigma z will be equal to 0. This condition can be achieved by its proposition is now uniform set distribution sigma z dash equal to C3, so that the resultant force is equal to 0 itself. Now for solid cylinder, what happens? The resultant of sigma z will happen from 0 to r to pi r into sigma z. Pi r is the circumferential radius, length of the circumference at a distance r multiplied by the thickness dr at that of the ring there, and multiplied by the sigma z longitudinal stress. I have to integrate from the 0 which is at the center and p at the outer radius, which is supposed to be equal to, if we put the value of sigma z, then this equation will take this particular form 2 pi alpha e, again 0 to b tr and 2 pi sigma e c1 and 1 minus gamma 2 etc. pi d square itself. This resultant of the superimposed uniform stress will be sigma z dash equal to c3, that is pi b square, area of the disk itself, outer area, total area of the sieve itself multiplied by c3. The value of c3 makes the total for 0 in z direction is therefore c3. We put the value of c3 here, and And this equation on the right side here will take this particular form like this here and here and here. So resultant stress distribution along the length will thus result in this right hand portion, and with the integrations, all of the integration alpha into E 1 minus nu 1 by b square divided by 0 to 2 tr into r minus t. Yes, ur is the displacement given is if that's displacement is then given by the equation plus minus gamma cr c1 r by 3. Now, next question is hollow cylinder with radius r. Here, cylinder have a inner radius r. We should doubt the solution. Please from the stress result again. We use the earlier equation we have already made, putting E1, V1, sigma 1 in case of E, V and 5, then converting according to the 25 equation number. Then we are just having sigma r 1 minus square root 1 by r square minus a square minus a square, integration transform a to b tr or a to r tr instead, or sigma theta sigma into 1 by gamma 1 by r square plus a square divided by b square minus a square 0 a to b tr a to r tr minus tr square itself. And displacement also given by this equation in the similar manner, and we get sigma r radial displacement, sigma theta radial displacement, and sigma z longitudinal stress. Now let us go on through another practical problem. What is given here? The inner surface of a circular hollow shaft is at a temperature Ti. Hollow tube is hollow. Here, tube is hollow, and inner surface is at temperature Ti, and the outer surface is at 0 temperature, just opposite in the earlier expression. Assuming state condition, I calculate the stresses. Where is the value of sigma theta and sigma g near inner and outer surface? So this problem is exactly opposite to our earlier discussion, where we have that there is no temperature at the inner end and maximum temperature at the outer end. Here we are saying that outer surface has no temperature and lower surface has temperature Ti, means T inner. So under steady flow condition, the temperature at any distance up from the set given distance is given by this expression itself, where T is equal to given Ti temperature at the inner divided by log B by A multiplied by log B by R, where T is the radius at the outer surface, A is the radius at the inner surface, and R is the temperature of a radius of a constant radius, where we are what whose T is going to calculate itself. Provided we know Ti, the temperature at the innermost surface, we know B, the radius of the outer surface, and know R, radius of the inner surface itself. If we use this value of T in this equation, 36 to 39 from this all four equations from here, here, and here. We replace T here, T here, T here, T here, and T here by this particular value of T itself. So this equation will take this particular form: alpha E T1 1 minus nu log B by A minus log B by R minus A square by B square minus A square. So minus 1 by B square divided by R log B by A. Similarly, by putting the value of T, sigma theta, the circumferential stress will be induced by this relation, provided we know the radius R, which we are point of consideration along the radial direction. Here sigma R, all other factors alpha E, Ti, and nu, B and A are known. We have to know the value of the radius R, which will give us the temperature, stress, thermal stress at a point at a distance R from the center itself. So we have got thermal stress at the radial direction, thermal stress at the circumferential direction, and thermal stress at the longitudinal direction itself. If sigma is equal to r at the innermost part of the radius, but at the center of the axis of the radius, and r is equal to 0 and r is equal to p, the stress component of theta and r, theta and theta, sigma theta, sigma j, attain their maximum positive and negative values are r is equal to a and r is equal to p. So both them will have maximum positive at the innermost radius of the cylinder and outermost radius of the cylinder itself. Innermost maximum positive and maximum negative is the outermost. So sigma a, we put the respective value of r is equal to a here and r is equal to b, and when at the inner, when r is the means radius at the innermost area, we put r is equal to a and take whole equation will take this particular form, and in r is equal to b, the radius at the outer portion of cylinder, whole equation will take this particular form itself. If Ti is positive, means temperature is increasing, not decreasing, the radial stress is compressive in all directions, where sigma j are temperature at the inner surface and tensile always at the compressive at the inner surface and tensile always at the outer surface itself. These tensile stresses cause cracks in the brittle materials such as stone, brick, and concrete itself. Now let us see what is exactly happening in the sphere itself. We shall now consider the problem of a sphere. It is subjected to purely radial temperature variation. That is, temperature is changing along the radius. That is, T is a function of R alone. Temperature changing, temperature will change along the radius. So T depends on R. Now, because of the symmetry, the shear stresses are all zero, and the normal stresses are such that sigma theta is equal to sigma r. As it is a sphere, the circumferential stress is equal to the radial stress. For sphere, shear stress equal to radial stress. Now, this equation equilibrium in the radial direction is then, we have already have this equation 1 by r d by dr r square sigma r minus 1 by r sigma theta, or we have d by dr 1 by r sigma r multiplied minus 2 into r sigma phi itself. The stress regulations are 1 epsilon r 1 by e sigma r minus 2 into nu into sigma theta plus alpha theta itself, and sigma phi is equal to sigma theta is equal to 1 by e sigma phi minus gamma sigma r plus sigma phi itself, and plus alpha into t. So radial stress is depending on the radial stress as well as on the circumferential stress in the direction, which may be same, but here we are same, but their effect will be always exist. And epsilon phi, the stress strain induced in circumferential direction is epsilon r into minus 1 by e 1 by sigma r minus mu into sigma r and sigma phi plus alpha t itself. Now with these two equations, if we solve for sigma r and sigma theta, then sigma r is 1 by 1 plus nu, 1 minus 2 into nu, 1 minus nu plus epsilon r itself. Epsilon plus 2 into nu epsilon theta minus 1 minus nu alpha into r. And similarly, sigma theta will take this form, the same in the first one, plus phi, isolated along phi, circumferential direction, nu into epsilon r minus 1 plus nu into alpha r into t, alpha into t. from strain displacement, what we know, strain displacement relation, we know radial strain is the differential of displacement UR or rate of change of UR divided by the original radius, and epsilon phi or the circumferential stress epsilon theta or epsilon phi is equal to UR by R, where UR is the displacement along the radius and R is the original radius itself. Then if we substitute this value of sigma and sigma theta, then substitution of this in the equilibrium equation, we get this particular d square UR by pi d square plus 2 by R DUR plus dr minus 2 by UR by R, which is equal to 1 plus T divided by 1 plus 1 minus T itself into alpha into D into T divided by dr itself. This can also be written by taking the differential sign outside by 1 by R dr by R R square UR, and right hand portion remains same. So solution is, what is UR is the integration of whatever alpha into 1 by R to 0 to R dr square into dr plus C1 R plus C2 R. Again we got the two constants C1 and C2, and it is to be determined from the boundary condition itself. The lower limit of C1, the lower limit of vertical diameter is supposed to be 0. The sphere is solid and equal to A outer and equal to A the outer radius, and the sphere is hollow. Now from the expression of UR, the strain component XR and XR theta can be determined for 42. This is this equation, and substituting the XR in 40. So from epsilon theta, from this equation we are getting epsilon and epsilon theta, and put this equation is here and epsilon and epsilon theta here and here is that. What we have then, the strain component epsilon and epsilon theta, epsilon phi relation substituting in 40. So that sigma R by sigma theta equals sigma phi is the value, this equation after putting this value of respective point is over sigma theta, and sigma phi is putting the value of respective point itself. Now we shall consider two specific cases. What is a solid sphere? In this case, the lower limit A in the integrals may be taken as 0. In equation 4.9.43, the limit becomes minus 1 by R. That is the once upon we have decided this equation is equal to 0 itself. And according to L'Hospital's rule, consequently, the constant C2 will be equal to the 0, as otherwise the displacement UR will become infinite and R is equal to 0. The same process is following here also, and the C2 is going to be 0, and the constant CR is defined sigma R is equal to 0, sigma R is equal to P, and R is equal to P. So from equation alpha 2 alpha P divided by 1 minus nu into B multiplied by 1 by VQ is equal to 0 to R 0 to B T R square into dr plus E3 R C1 is equal to 0 by 1 minus 2 theta. From here we are getting C1 in this equation, and if we put this value of C1 and C2, we get the value of sigma R like this, and sigma theta like this. So this is the value of radial stress in in hollow cylinder, and circumferential stress in plane cylinder itself. And in case of a hollow cylinder, here radius A is the radius of the inner cavity, and B is the radius of the outer cavity. The boundary condition, of course, sigma R is equal to 0 at R is equal to A. At the innermost, there is no stress, and at outermost radius, there is no stress, no radial stress. Thus, this equation 44 reduced to E by C1 minus gamma minus 2 into A into F star by 1 minus gamma plus 1 by AQ. And the equation, the different equation for equilibrium becomes like this: E by C1 minus 1, etc. When we are here, we have to solve C1 and C2. And this equation can be used to solve C1 and C2 by substituting this value of equation 44 here. This is CR. And the result will be sigma R like this. Here we have with the value R1, execution is from A to B, inner to outer radius here, and we get at phi the circumferential stress, and with this particular equation, where at a distance R from the center itself. Therefore, stress can be calculated with the distribution of temperature is known itself. So let us stop here. We'll start the next portion after your exams.